This is a 2024 updated version of Balancing Chemical Equations, so you should have a notebook with you. You should have this handout. If you don't, that's okay. I'm going to be moving as quick as I can, and that means that you have got your finger on the space bar, so you can pause and rewind this video anytime you can. I will ask you to pause and at least think of a few things as we go. So I'm just going to read through the notes at the moment. We're going to get into it in a second. So, some background information on how to balance a chemical equation. First, it leads into the law of conservation of mass. So, a chemical reaction occurs when two molecules collide in space and chemical bonds are formed and broken. These are shown using chemical equations. So, on the left side, we have the reactants, and on the right side, we have the products. The reactants or products are separated by an arrow to represent a chemical reaction. So the arrow is right here in the middle. This is an unbalanced equation, and we will get into that in a second. So the law of conservation of mass will state that the total mass of the reactants must equal the total mass of the products for any given chemical reaction. So the mass of the reactants added together must equal the mass of the products every time, all the time, because that's the law. Now, you may hear of it as that matter cannot be created or destroyed, but I do like this definition a little bit better because it applies to what we're talking about a little bit more. So if we have 50 grams of hydrogen and 45 grams of oxygen, you guessed it, there should be 95 grams of water produced every time, all the time. All right, we'll get into this example in a second. I'm going to show you a few different quirks about a chemical reaction. You should know that an element is a capital letter, sometimes followed by a lowercase letter. It doesn't always have to be followed by a lowercase letter. So if you have a capital letter H, that is just hydrogen. But if you capital letter C, followed by a lowercase letter L, this is chlorine. So this would be hydrochloric acid right here. You have a capital letter Z and so forth. So on the left side, remember that we have the reactants, and on the right side, we have the products. Good. Now you may notice some parentheses with letters in there. These all mean something. You notice that there's numbers in front. You notice plus signs. We notice arrows. And we notice that sometimes there's things over the arrow. So we're going to get into all of that. If you have a letter for a subscript, remember Superman rides the subway. So in the subway is on the bottom. So the superscript is on the bottom. And if you have a letter there, it is going to tell you the state of matter. So a solid, liquid, or a gas. AQ stands for aqueous, which means it's dissolved in water. For example, hydrochloric acid is dissolved in water, or zinc chloride is a salt that is dissolved in water. Now, if you have a subscript that is a number, that number is telling you the number of atoms that are in the molecule. So, for example, we have H2, so for two hydrogens. Now, the arrow means to produce or yield, and then the triangle is the Greek letter delta. It stands for heat. Or if you have a chemical symbol, normally we won't write an X, but if you had a chemical formula or something like manganese dioxide or some kind of element, that is used as a catalyst. A catalyst is not actually used up in a reaction, so it doesn't belong on the left or the right side, so it does make sense to put it in the middle. The plus signs are just adding those things together, right? It means that they're combining with each other. And then the last one is going to be the coefficient. So just like in math, the coefficient is going to go in front, and that's going to tell you how many of this molecule we have. So if there's no coefficient here, then the coefficient is 1, and that means that we have 1 zinc chloride for every 2 HCl's. That's kind of what that's telling us is going on. All right, I want you to pause for a second and tell me the sum of the coefficients in this chemical reaction. All right, did you say 5? Because that is correct. There is the coefficient of here is 1 plus 2 plus 1 plus 1 is 5. Very good. So now the law of conservation of mass does say that the mass of the reactants must equal the mass of the product. So 50 plus 150 will be 200. And then 125 plus a unknown amount must also be 200. So they must also be 200. So by simple subtraction, we can figure out the mass of zinc that's right here. What we can do is, since this one, it has to be 200 overall, and 125 of it is calcium carbonate, then zinc must be the stuff left over. So 200 minus 125 will be 75 grams. All right, we can do the same similar thing with sulfur and iron. That will make iron sulfide. Remember, if you're adding heat, what symbol do you write? You put a delta right there. So if we have 56 grams of sulfur, and we don't know the mass of iron, but we do know that we made 83 grams of iron sulfide, we can figure out the mass of iron that was made. All right. So there was 83 grams on the product side, so there must be 83 grams on the reactant side. Simple subtraction, and we get 27 grams. Side note, this only works for mass. This does not work for moles or volume. This only works for mass. When an iron nail rusts, it gets heavier in mass. Does the iron nail follow the law of conservation of mass? You bet. Everything must follow the conservation of mass. How so? Think like a chemist. It went through a chemical reaction to go from here to here. What must be added to actually do that? Well, remember that there is oxygen in the air. So we had oxygen come in and get added to that nail. And so the mass of the oxygen from the air increased the mass of that nail. Very cool. Now, one last little quirk is that if we add 50 milliliters of isopropyl alcohol and 50 milliliters of water, we add them together and the volume is 98 milliliters. That is quite a little quirk of science, is that volume is not conserved. We cannot add 50 milliliters and 50 milliliters and get 100. That doesn't work. All right. And the reason for that is the molecules are so small, but mass will always be conserved. So if we find 39.5 and we add it to 50, we should find that the total mass of that solution at the end is 89.5. Volume is never conserved. That's because the molecules are so small they can compact a little bit together. All right. Now we're going to look into how do we balance chemical reactions. Remember that the number of atoms on the reactant side must be the number of atoms on the product side. This is the law of conservation of mass. You can't cut away or destroy any atoms. So we have one black sphere here, and we have another black sphere here. So there is one carbon on the left, one carbon on the right. There are 4 hydrogens here. 1, 2, 3, 4. There's one hiding in the back. And there are 4 hydrogens here. All right. There are 4 oxygens here. And there are 4 oxygens here. See that? So all the atoms are balanced. You'll notice that there's a 2 in front of oxygen because we had 2 molecules of oxygen. We had to add in another molecule of oxygen for every 1 molecule of CH4, and that's kind of what we're getting to the next theme of the next couple of weeks. For we had 2 oxygen molecules for every 1 methane molecule. So, a couple of rules for balancing reactions is to always leave the subscripts alone, only add coefficients, that's the numbers in front. If you have the same polyatomic ion on both sides of the equation, balance them as a single unit. And then always balance singular atoms or molecules last if you can. So another little thing is that sometimes I will see this when people write their balanced equations. Now, this one is technically correct. However, this is better. All right, if you can reduce it, please do so. So this is no good. This is better. Now, we would normally just not write the 1, so we would just write 2 and then a blank spot and then a 2. All right, so how do we do this? We have 2 hydrogens, 2 oxygens, we have 2 hydrogens here, and 1 oxygen. So, since we only have 1 oxygen but 2 oxygens over here, see how they're not balanced? I got to balance this guy. So what I'll do is I'll put a 2 in front. Now, the side effect of that is that it unbalanced my hydrogens. So now I have 2 times 2, so that's a total of 4 hydrogens. So that means I need 4 hydrogens on the left to make sure everything balances. Then we're good. All right, so that one's fine. Now, if you look, I am doing the ones that are in your handout. So these are at the bottom. If you do not have your handout, go ahead and scribble them down in your notes, pause and write them down first, and then balance them as I go, please. So we have SiO2 plus Mg makes Si and MgO. We have one silicon. All right, so we're good. 2 oxygens, only 1 oxygen. Okay, so we're going to have to take a look at that. And a magnesium and a magnesium. Okay. So, all right. So the thing we got to do is we got to make sure we put a 2 in front of here to make sure that our oxygens will balance out. All right. Now we unbalanced our magnesium, so we're going to put a 2 in front of that. Okay, doke. Let's try again. We have magnesium, HCl, and that makes magnesium chloride and hydrogen. So we have magnesium. Magnesiums look okay. They're going to balance 1 to 1. All right. So we have hydrogen, 1 hydrogen, but only 2 hydrogens over here. We have 2 chlorines and 2 chlorines over here. So the easiest way to balance that is to put a 2 in front of this, and it falls right into place. So you'll notice a theme that they should start falling into place. If they're not, then you probably want to start over. All right, don't try to keep fixing your mistakes. Just start over and start fresh. All right, a couple of tricks of the trade. If you see a 2 and a 3, the magic number is 6. So what I mean is, so we have a 3, we have a 2, and we have a 3. Well, the magic number is 6. We want this to be 6, and we want this to be 6. We want this to be 6. So how do I make that 6? Put a 2 in front, right? How do I make that a 6? I put a 3 in front. All right. So now the oxygens are balanced. Now we have 2 potassiums and 2 chlorines, and only 1 potassium and 1 chlorine over here. So easily we can just throw a 2 in front and we're good. All right. Now jump down one. Let's see, Al2O3, Al2. There's that 2 and 3 thing again. All right. So 2, 3, the magic number is 6. So let's put a 2 in front to make this 6 oxygens. Let's put a 3 in front to make that 6 oxygens. And 2 times 2 is 4. So there's 4 aluminums here. So that one's 4. All right. Combustion reactions. These are fun. These are actually pretty easy if you know the theme for them, because they're always the same. Now, a combustion reaction will have a carbon and a hydrogen, usually on the in the front, and you'll always be adding oxygen. That's what makes it a combustion reaction, all right? Because when you combust something, you are chemically adding oxygen. You always make the same 2 products, carbon dioxide and water. So the only thing that changes is this guy right here that I'm going to put a star on. So basically, what I like to do is start with the carbons first, and then I do the hydrogens. Make sure you save the oxygens for last because that's your singular molecule, all right? So let's balance the carbons first. There were 2 carbons, and there are 2 carbons now. Now there's 6 hydrogens, and there's only, let's see, so to make that 6 hydrogens, let's make that a 3, okay? And now the key here is that if we look at oxygens, you have 2 oxygens. No, wait, I lied to you. 2 times 2 is going to be 4. I have 4 oxygens. And then 3 times, that's going to be a 1. That's going to be 3 oxygens. All right. So over on the right, we have 7 oxygens total. So we need 7 oxygens over here. The easiest way to do this is to make that 7 halves. All right. Because the 7 halves times the 2 is going to just make that 7. I'll just take the 7 and then divide it by 2. So the number of oxygens on the right divided by 2 will be that. All right. And then you can leave it as 7 halves if you want, or multiply them all by 2 to get all whole numbers. And so we would get a 2 over here. That would be a 7. And then 2 times 2 is 4. And then 3 times 2 is 6. All right. So that is the best way to do a combustion reaction. You may want to go back and check that one out, but they are all the same, the exact same method every time. Do carbons first, hydrogens second, oxygens last, and then just always put the number of oxygens on the right divided by 2, and that is your coefficient for oxygen on the left every time. All right, so polyatomic ions, balance them as a unit. Here we got a polyatomic ion, a PO4, right? And so we've got another PO4 right here. Please don't break them up. Just think of 2 PO4s, and then 4 PO4s, all right? So think of them as kind of like your own unique element if you want. So look, we've got 1 silicon and 3 silicons here. So I would recommend putting a 3 in front. All right, it should work. Now, since we unbalanced silicon, let's figure out the partner that it's with. So 3 times 2 is 6. So there are 6 oxygens. I'm not going to look at these oxygens here because they're part of my ion. So I'm going to look at this oxygen over here. I want to make this 6, so I'm going to put a 6 in front. My animation's messed up. I'm going to put a 6 in front, all right? Well, I want 6 magnesiums right here. So that means I want 6 magnesiums here. There was a 3 right here. So you guys already saw that there's a 2, all right? So 2 times 3 is 6, so that seems to work. And then 2 times 2 PO4s is going to be 4 PO4s. And look, I have 4 PO4s on the right. So like I said, these things should kind of fall into place as you were doing them. All right. So if we take a look at the next one, this one is a polyatomic ion as well, right? Sometimes people get messed up by water. You can kind of uncross out water and make it HOH. So you have the OH here and you have the OH there. So you can kind of think of it that way. And then you have SO4 and SO4. So you will need 2 potassiums right there and 2 potassiums. And then you will need 2, because we had 2 hydroxides there, that must mean that we will need 2 hydroxides here, right? And since its partner, there were 2 hydrogens here, that's because we have 2 hydrogens here. You see how this is kind of working? Now, another way to think of it is, I like to think of them as an acid-base reaction, because this is an acid and a base. This is a base, and this is an acid. What makes it an acid is the fact that it's got hydrogen in front, and what makes this a base is because it's got an OH in the back, and the hydrogen and the oxygen are going to make water. So if we have two acids, like there's two hydrogens, two acids, and you only have one base, what you actually want to do is make two bases, right? So two acids and two bases will make two waters, and that should balance everything for you. All right. So that's the way I like to think of it as well. All right. So, real quick check for understanding. Do you know all the different pieces of this chemical reaction? Pause the video for it. Okay. All right, whatever. Just teach me, Russell. So we've got on the left side is the reactants. In the middle, that would be your catalyst. Okay. That would be the reaction arrow, or produce or yield. And on the right side is the products. You know what all this symbols mean, and you know what all the subscripts mean, and you know what all the coefficients mean. All right, so we finished all the notes. Now here is our practice. Now, just in case you didn't get it, you should have a practice sheet with you, and I want you to be able to go through and make equations and balanced equations for all of these. So pause take a picture of it real quick and copy them in your journal if you don't have the handout, or if you do have the handout, work directly on it. All right, and then as an added challenge, I do expect y'all to be able to do this. So I want you to write equations in your own notebook. All right, now this is going to take your highest brain level, because you're going to need to use the correct nomenclature to be able to write them out. But do the best you can, and don't forget to balance them at the end. Couple of hints. Look at these. Here are your combustion reactions, right? There's a combustion reaction here, here, and here, right? Don't forget to balance your polyatomic ions as a unit. So there's a hydroxide. You can think of this as HOH if you want. Polyatomic ion, right? There's your OH and your OH. Okay. Let's see if we can find, here we go. This is an example of the 2 and the 3 magic number, right? Let's see, and another 2 and 3 magic number down here. Okie doke. Hopefully will help you get through and figure out all the good stuff. All right. Have a great day.